then, please, which will be from Kevin Haninger. Have I said that right, Kevin?
I'm pretty sure.
I should know by now, shouldn't I? Okay. So Kevin is a staff scientist at Fraunhofer IPK in Berlin, working in mechatronic design for impedance control, compliant robotics, and human-robot interaction. He completed his BS, MS, and PhD in mechanical engineering at the University of California, Berkeley, under the supervision of Professor Masayoshi Tomizuka. He has previously worked at Franke Amica in Munich, at the Space Robotics Lab in Sendai, and consulted for Gate Labs in San Francisco. And I'm happy to work with him and others on the Sherlock project. So thank you, Kevin. Over to you.
Thank you very much for the nice introduction. So today, the title of my talk is Flexible Assistance and Mutual Understanding. And here I have really just one question in the center of it, which is how can we make robots which are responding to humans, adapting to humans, and being flexible with humans while still being understandable and predictable to the humans for both practical reasons so that the performance is good, as well as for human acceptance. So I'll start by giving, there we go. I'll start by giving my idea of what the industrial human-robot interaction today looks like. And we have human-robot interaction being used in factories. And the big advantage is that the robot cells are open. You don't need to install the fences in certain cases. And you can do multiple tasks, but most of these tasks are in parallel. So the human is doing some tasks that you can see here, some fine manipulation tasks, and then the robot is working in parallel, and the robot is slowing down or stopping according to certain safety conditions, and allowing the human to move freely, and then continuing with the activity once the human is out of the way. So the human is doing basically what the robot can't do. So any sort of fine manipulation tasks, parts that are hard to grasp with the robot gripper, doing any wiring or manipulating any flexible materials, doing click assemblies or really contact-rich manipulation, which is either difficult or not really possible to program a robot to do. And then the human is also doing things that the robot is just too expensive to do, where the costs of commissioning and programming the robot to do them are just too high. And there we see, especially in low volume production, where the task is changing a lot. And then we see this also in tasks where there's a lot of variation in the position of the parts, and you would need to either introduce a lot of sensors or add a lot of fixtures and constraints to the environment to make the task more structured. And so I would say that the human-robot today interaction that we see in factories today has very limited flexibility because it's designed so that the robot task does not change. The way that the robot is responding to the human is slowing or stopping, and in some cases, moving around the human to continue with its tasks. So how can we make the robot more flexible? We want, especially today, a common topic is flexible manufacturing. We want to make it easier to bring automation into a wider variety of applications. And a lot of these applications don't have automation today because they are semi-structured or unstructured, where there's too much variation. The two standard solutions that you see today for helping a robot to respond to the current state of the cell or the current needs is you have some sensors which are measuring the state of the cell and then using that to modify the robot program. Or you have some centralized factory control system, which is processing orders or some list of products to produce for that day and producing a change in the robot program. And sometimes you see a mix of these two, but in general, both of them increase the complexity and cost of the robot solution and the automation. So the alternative that we all know is that we can use human-robot interaction, where we have local sensors in the robot cell, or we have some interfaces. And with these, the human is producing some signals which are modifying the behavior and the plan of the robot. And then the robot may have some displays, lights or augmented reality glasses that are worn by the human, or additional displays that are in the environment. And with this, the robot is displaying information back to the human. So these inputs to the robot allow the human to change the behavior of the robot. And then the displays allow the human to understand the state and the plan of the robot. So we can write these out a little bit more. So we have the two agents here. Each of them knows some things for sure, and they are maybe estimating some things of the other agent. So the human knows, in this case, the task state. It knows what parts are currently there, what the current product order is, how this task is different from the tasks before it. And the human, to a degree, knows his own state, his intention, his goal, how fatigued he is, all of these internal human states. And the human is estimating, for example, the robot state. What is the internal state of the robot? At what stage of the robot program is the robot in? Where will the robot move next? And then on the other side, the robot also knows some things and is estimating other things. So the robot knows its own state, the positions, velocities of the robot, the immediate values of any sensors that are connected to the robot. And then, especially if we're making flexible robots, the robot is estimating some things. It's estimating, for example, the state of the task, what has already been completed, what's coming next. He could be estimating the human goal or intent, and he could be estimating other states of the human, such as human fatigue. And the idea in flexible human-robot interaction is that we want to use these estimated or inferred properties to change the behavior of the robot to better respond to the human or the task. So we have our two agents, and then we can talk about mutual understanding and predictability. So for each agent, they have the things that they know at a moment in time. They know their own goal. The human knows the robot position when he can observe it visually. And he may know any information which he gathers from the displays. And then this, combined with some understanding or expectation of the robot, allows him to predict the future state or the future trajectory of the system. So that means the robot as well as the state of the task. And the uncertainty of these future predictions are the predictability. And predictability has been shown in a lot of ways to be important for acceptance. Predictability is important for control too, when we just write algorithms to try and make a process do a certain thing. And the one-directional predictability has been studied in human-robot interaction. So we have some techniques which formalize how well the human can estimate the robot's goal. And then we have a lot of work which is looking at how well the robot estimates the human state. But my claim here is that we need to consider the coupled behavior of the two agents. So for two motivating problems, we have a co-manipulation task on the left where the human and the robot are moving a table, and they need to move to the right here, but there's an obstacle there, and a decision needs to be made about to move to the top or to the bottom. And the robot, when it's trying to plan about whether he should move to the top or the bottom, this plan is depending on his expectation of the human and the future or the expected future behavior of the coupled system. You can see this in a classical example of two people meeting each other face to face who need to pass each other. And it's the shuffle back and forth where nobody knows which side the other person will take. And then once somebody makes a decision and communicates that, then the other person can plan around that. And the plan of the agents is depending on each other. So the future state depends on the coupled behavior, and my claim is that we need to consider the coupled behavior to formalize predictability. So for a concrete example, we can look at this exoskeleton assistance here, and there are some sensors. We have IMUs on this exoskeleton here, and we use this to estimate the current state of the task. And then based on that, we apply some assistance with the exoskeleton. So we can train the classifier on the IMUs, and then we can collect the data with the exoskeleton powered off, and then train the classifier, and then use the classification result to apply assistance. But when we do that, the exoskeleton is changing the behavior of the human. It's making it easier for him to lift his arm. And actually, in this case, the performance of the classifier dropped by about half. And it was not really usable because the assistance from the robot was changing the observations that the robot was making. So in this case, we had a specific solution of just collecting data with mixed assistance and training on this, and that was sufficient, but we needed to think about how the coupled behavior is changing. And a more general approach, in my opinion, is using uncertainty-aware planning on the side of the robot. So the robot, in this case, would have some idea about how confident it is in what will happen in the future. And this can allow the robot to wait when it feels it doesn't have enough information or enough confidence, and it can wait to gather more information or to ask for more information from the human. And there's a lot of ways that we can formalize the uncertainty. What we do here is we have some discrete uncertainty. So there are one of a discrete number of tasks that can be happening in the cell. And the robot could have anywhere from no idea about what the current state is to a very confident idea about what the current state is. And then the idea is that we plan based on this confidence in order to provide flexible and active assistance. So here we use Gaussian processes. We don't need the details, but this is a model which allows us to see the uncertainty in our model for the human. And then we use this uncertainty to predict the future behavior of the system, of the coupled trajectories. And then we can have two ways of planning. We can minimize the expected cost, which is the cost of each possible mode weighted by the probability that that mode is true. Or we could have risk-sensitive control, which is where we weight larger costs more because they're being exponentiated and are growing even larger. So we have this online planning. The video is not working. There we go. Okay, so the in this case, we have just one mode, which is the goal is to mount this plate onto this system with the pins that you see on the left. And in this approach, the robot is able to flexibly plan because it's resolving this planning problem online. So even if the human is moving the robot to a new position, the robot is trying to do the parts of the task that it recognizes, even though it needs some assistance from the human to do the fine positioning at the end. Then we can extend this to have two modes where the human needs to move the plate either to the left onto the pins or to the right onto this yellow table. And in this case, we can compare the average cost with the risk-sensitive control. So the robot starts in the middle and it has a 50-50 belief about which goal is current. And when it's taking the expected value, when we start the robot starts to move downwards and forwards in the middle here because that's a path which is okay for both of these tasks. And then once the human moves it towards a specific goal, the robot understands that that goal is active and then provides better assistance moving towards that goal. When we do the risk-sensitive control, in this case, the robot is started, but it's waiting until there's more confidence in the goal before providing the assistance and doing some motion of its own. So in this case, the robot waited until it had the confidence that the goal is actually the pins on the left, and now it's providing the path planning according to that goal. And then here we just do an example where we change the goal online. So we start to move first to the pins, and the robot is getting close to the pins, but still needs some fine positioning. We can do this task. And then here we're changing the goal online. The robot is responding to the human forces. And then here it's confident that the goal is to move onto the yellow table, and is providing some assistance there, and is even replanning online to continue to move towards the yellow table. So in my opinion, the risk-sensitive planning has some advantages for flexible human-robot interaction. We can get some desired behaviors to emerge, such as waiting when the risk is too high or uncertainty is too high. We also have smooth transitions and assistance between discrete modes. But on the downside, this is generally less robust than having an explicit interface like a button which says move to the left or move to the right. And if we do traditional trajectory planning that is not considering the uncertainty or the risk, typically it's faster, at least with the techniques available today. So that was a quick introduction to risk-sensitive control for the flexible and predictable online planning. Thank you to all of you, as well as the collaborators that have helped with this work.
Thank you so much, Kevin. Really fascinating bit of work there. And I'm really, I'm going to hand over to some questions, but I have a burning one of my own, really, which is a sort of double-edged question, which is, firstly, what's more difficult for you in terms of, is it the robot being able to predict the human intention, or the human being able to predict the robot intention? And added to that, is that human forces direction, is that the only way, or are you working on other ways of informing the robot to changes of decisions that it needs to make and planning that it needs to make?
Good questions. So the second question, yeah, right now we use forces because that was the easiest first place to test this. And then this is also kind of a dynamic task, which fits nicely to the framework. Obviously, there's a lot more applications in human-robot interaction where there's no contact, where you're doing workspace sharing and need to replan the robot trajectory there. I think it's a good direction for future work. Right now, we're hoping to test the algorithms and the easier setup for us. And then the first question, if you could remind me a little bit, sorry. I think you're muted, Sarah. Sarah, you're muted. Is her audio on? Is my audio on?
It's my audio. I've done it again. I'm great. I'm great at that. Yes. So sorry. Yes, it's a mean question. It's the one about what do you feel is easier, human predicting robot intention or robot predicting human intention?
Yeah, probably it depends on the application. It's hard to make any general statement on that. The amount that the human behavior changes based on the robot depends on the task a lot. But at least for me, it's the human intelligence and ability to kind of understand, especially after a couple trials, the robot makes it easier for the human to understand the robot. But
thank you. And that slide you've just got up there typifies for me one of the biggest problems with my sort of research, in that we can find out, like the speed trust rule, we can establish some rules of behavior, but they may change over experience with a robot. So anyway, I'm hogging you. So do we have any other questions, please, from the audience?
Yes, I do have.
Go ahead, Andre.
I'll show my face just in case. No.
Yes, do that.
Sorry. So this is quite nice story, and like this style of robot training or robot-human interaction instead of programming and so on and so on. But there is a few questions to make sure I understand clearly what kind of activities are happening in this way. So one possibility is, which I'm not sure what you've seen, is that one kind of programming or creating a movement pattern or adjusting or guiding the robot arm system to execute a specific movement pattern, performing a task. Yeah, that's one thing. Okay, then if that is one of the example, one of the tasks you are using, saying there are some basic issues arising, such as some adjustments. If it's a really fine, accurate task, it has to be, always, the setup should be the same, no error allowed, especially high precision manufacturing or whatever. So how the robot is dealing with is this robot kind of creating an image or picture or situation of the goal to achieve at the end of the compliant training, or what's happening? How is it ensure that the task is always solved regardless of some noise and errors or
so right now that's solved from the human. So the robot takes over the repeatable parts of the task. So we have some demonstration data starting from 3 different positions, and the human does the task, and we model the human forces over position. And this gives us a rough model for the task, in this case, plus minus 2 centimeter or 3 centimeter. And the idea is that the human then comes at this last part to provide the final fine positioning, because there may be just a little bit of error in the model or some variation in the task.
So the robot is not trained to do the task without human interference. Yeah. In this
case, no.
The final adjustment is done by the human.
Yes.
Okay.
Okay. Do we have any other questions for Kevin?
I would have one if there is still time.
Yes, there is time. Yes, we're slightly ahead of time. Go for it, George.
Okay. Hello, Kevin. Just a short one. I saw in the beginning of your presentation that you also talked about some flexible components like the cables and the clips for inserting. So for me, it's a very particular and very interesting case in the sense that as far as I can understand, the force control that you showed before, the impedance control, will not really work that much if we're not talking about a stiff object that we may need to manipulate with the robot. So my question is, does your method or your strategy support also including data coming from sensors other than the force torque control? For example, maybe some external sensor observing the behavior of the flexible material and still being able to apply a similar strategy for the robot to operate?
It's a good question. I think in the case of the flexible materials, they have some domain-specific solutions that they use. I don't know if they use uncertainty, but they do use vision systems like you mentioned or suggest. But another example is we have an ongoing project right now where we are using the robot to verify that the click connections are correctly inserted. And there we do use reasoning about the uncertainty. If we can't classify if that was successful or not, then we ask for the human and get some more verification of it from the human and use that to improve the classifier. So still using the uncertainty motivation, but of course the applications are very different and the solution is not using model predictive control or the necessarily the impedance control or force control.
Mm-hmm. Okay. But do you think that it would be possible, for example, to apply in the case of routing flexible components like cables? I mean, to have the robot being able to execute this strategy for assembling the flexible part and still being compliant, let's say, to external input as well?
Yes, and they do also use force control in, for example, the cable trees, like here, the cabling, so that you can pull the cable tight with the robot, for example. And then being able to respond to external forces, like the human correcting the robot positioning, is also a nice potential application to the flexible materials.
Okay, that's great. Thanks a lot for clarifying.
Yeah, thank you.
Thank you. That was really useful. Anybody else got a question for Kevin? I bet they have really, Kevin, just saying. All right. In that case, we're running slightly early. So thank you very much, Kevin. Thank you. That was really, really interesting and really easy for me to understand, which is